We so our speaker is Jordan Lind, who is the co-founder and business development officer of a company called Clear as Water. That what they do is they make algae-based biological nutrient removal systems for wastewater treatment. And it's a very novel technology that they've brought to market, and it's fully commercial now, and they have a number of installations. But I know it's been a passion project for a long time. Jordan and I first met each other through a friend of a friend, a mutual friend, and sort of got to know each other a little bit. And then some years went by, and we got reintroduced by another mutual friend, one of his board members, and realized that we actually knew each other previously. And so I'm gonna just turn it over to Jordan. It's a real pleasure to be able to introduce you, Jordan, and I'm looking forward to hearing your talk about the technology and all the trials and tribulations of bringing a new technology to market and now seeing it at full scale is pretty amazing. So
cool.
Take it away.
Thanks, Eric. I appreciate it. And likewise, I appreciate the opportunity to connect with you all today. I don't know how you guys work questions and answers, but feel free to interrupt me at any time today. Can everybody hear me okay? Somebody just, Sanjay, maybe give me a thumbs up. Yeah, okay, cool. So so today we're gonna talk about algae-based wastewater treatment design. We've recently gone full scale at a project in Western Wisconsin called the Village of Roberts. And we've got 4 other wastewater treatment facilities that are in full scale design and/or construction right now. So it's a really exciting time for this business, but more importantly, I think it's an exciting time in the engineering and design industry as we start to shift away from really what has been very linear design, especially in water and wastewater, to more circular design concepts and reuse. And so it's an exciting time. Our business was kind of at the forefront of leading some of that charge in terms of looking at wastewater industry and understanding that there were resources that were being wasted inside of these environments, really to helping to make the transition and enable resource recovery within a wastewater treatment plant, as opposed to just wastewater treatment and removal of what would be considered harmful constituents. So in terms of today, I just want to give you a little bit of background on the business, a little background on myself, nature as a resource for design concepts, typically referred to as biomimicry and biomimic design. We'll do a little bit on the advanced biologic nutrient recovery process overview so that you have a good sense of how that technology works. And then we'll actually apply it to a wastewater treatment plant. What are the lessons learned? What are some of the design fundamentals that we look at? And then overall, how does it get implemented into a real world scenario where you have hundreds of thousands, if not millions and millions of gallons of wastewater treatment that are coming from both households and industrial settings, and how do you design systems around that work and perform and have efficacy related to performance standards that are required. So we'll take a look at the first full-scale ABNR system in the world. It's pretty exciting. We just launched it about 3 months ago and are now in full production. So it's an exciting time. So just thinking about this was a company that I founded in 2008. And really, the idea was around sustainable wastewater treatment. Conventional methods of wastewater treatment are the application of mechanical processes like filtration combined with chemical addition, typically in the form of ferric chloride or alum or some type of metal salt. And while those methods have worked in the past, they were not as sustainable as I would have liked to seen in wastewater treatment. And in particular, what we looked at and we said, well, it looks like you're just taking what appears to be a water problem and you're transferring it to a solids problem, because now you still have to deal with the chemical and toxic sludges that get generated in the wastewater treatment process. And therefore you really haven't solved the problem. You've just transferred it from from a liquid problem to a solids problem. So how do we actually do this in a way that is more sustainable and solves the problem and stops the cycle? So the technology that we invented is referred to as Advanced Biologic Nutrient Recovery. Its acronym is ABNR. We secured the intellectual property in 2012 in the United States, some years later in Canada, and now have patents throughout Western Europe. We've got about 3.5 years of continuous flow treatment. We've done over 55 pilot studies and/or demonstration projects, and now we're in the full scale up of these large facilities that are treating municipal wastewater on a 24/7, 365 basis. From a performance standpoint, the technology doesn't mean much if you can't produce the effluent water quality needed to meet regulatory standards. This technology is best in class at hitting low-level phosphorus and nitrogen standards in the form of ammonia. When you start to think about this technology, it has a relationship that Mother Nature invented. We didn't invent. It's called the Redfield ratio, but it's the relationship of carbon, nitrogen, and phosphorus, and how that works in relationship to each other is basically the backbone of the kinetics and how these systems are designed. When we do think of design, we think of it as a specific phosphorus uptake rate that's applied on a mass basis. So there are different methodologies. You can do concentration methods, you can do mass bases. We selected mass basis, and this is pretty consistent with designing conventional systems in the wastewater space. So that's just a little bit of background. It's got 4 main components. There's a mix phase, a recover phase, a separate, and a harvest phase. And we'll talk a little bit about that in detail. But in order to establish why the technology is important, my experience as a serial entrepreneur and developer of technologies is that you've got to have a clear problem, whether it's a technical problem or it's a service-based problem. You've got to have a problem that is easily identifiable and that you've got a solution that provides valuable benefits. So in our case, when we looked at the problem in the existing wastewater infrastructure, whether it's in the United States or even more globally, historically we see wastewater systems that are very costly, they're very disposal based, they're linear, and they're energy intense. So they focus on waste removal as opposed to waste recovery or resource recovery. And they tend to be very cost centric. There's no revenue associated with it. They're chemical and operating expense intensive. They create forms of chemical sludges, which must be disposed of into landfills or other disposal methods. And overall, it's not a positive environmental impact. So that's one of the problems we identified. The second problem was poor water quality caused by nutrient pollution. So these systems, when you put too much phosphorus and nitrogen into receiving bodies, whether that's a lake, river, stream, or ocean, ultimately excess levels of that lead to a degradation of those receiving water body ecosystems. Those create health hazards, they create environmental damage, and they have significant social and economic impact. So we're working on a project right now for a lake in western South Dakota that every year gets an algae bloom, and the economic impact on that region is substantial. We're talking in the millions and millions of dollars for a very small community that relies on recreation and fees and tourists to support their local economy. So when we start to think about these systems, it's very critical to understand what's the problem we're solving. You'll note that nutrient pollution affects over 14,000 water segments in the US, over 2 million acres of lakes and reservoirs, and 78% of the continental US coastal areas exhibit some symptom of eutrophication, which is excess nutrients in those receiving waters. So thinking about this and why it's a problem, The old method of design was kind of take, make, and dispose. And we really wanted to transfer that to what can we look at that's regenerative in nature. And in order to kind of talk about that, you've got to have a different definition of what it means to be circular in nature. And for this conversation, I've defined it as systems that are restorative or regenerative by intention and design, with the primary objective to design out waste. And I think that's a critical component here, is designing out waste. The challenge that we have and what we had to address is that we have to take what we have today, which is disposal-based linear systems, and we have to combine that with innovative thinking around turning waste into value. And so the opportunity that generates is to leverage sustainable wastewater infrastructure to produce clean air, which is carbon recycling, clean water for reuse or discharge, and generate a valuable biomaterial, which goes into everyday products that we utilize. So that was really the foundation and the background of this technology. It was the problem that we identified and the opportunity that exists. And so ultimately, we then had to ask ourselves the question, well, where do we turn to for inspiration in this opportunity and thinking about this from a design perspective of designing out waste? Well, we turned to nature, right? And so I don't know if you've seen these experiences or these examples before, but Clearis ABNR is really a shining star in terms of what we would consider biomimic design. And biomimicry is an approach to innovation that seeks sustainable solutions to our human and industrial challenges by emulating what nature's time-tested patterns and strategies have done. So the planet Earth, even though we argue about its sustainability and whether or not we're moving in the right direction, it's 3.8 billion years old. So it has had to solve major challenges. So when we looked to wastewater treatment, we said, how do we solve this problem that we're identifying as excess nutrients and linear-based design? Well, we turned to nature. So some examples are the Japanese bullet train. That was originally a situation where it vibrated and made huge noises as it would exit the tunnels. Well, through engineering and design, they identified the way to redesign this and followed the method of the kingfisher, which ultimately led to a redesign of the nose of the system and eliminated all of the vibrating and excessive noise as these would exit these tunnels. Another example would be a Camp, the Italian sporting goods store that made ice picks based off of looking at a woodpecker and how they were designed and how they use their beaks. And then finally, another example here is the Coke Puron submerged membrane. These are membranes that sit inside of basically a tank, and they have a negative suction, a negative pressure circumstance where they're sucking water into these membranes and leaving the solids on the outside. What Coke looked at was seaweed within within the ocean environment, noting that it doesn't have headers on both sides. It just has a header on one side, meaning it's attached to the ground, and then the movement of the kelp at the top allows it to stay clean. And so they implemented this design. And matter of fact, it's the design that we use in our separation stage within our system. So we looked at nature and we said, if the problem is excess nutrients, then how do we use the concept of the result of excess nutrients, which is an algae bloom, to solve real world industrial and municipal problems? And that just happened to coincide, and this is pure luck, with a paradigm shift in the way that people think about wastewater treatment. I talked about it a little bit in the opening, but it's about in the past, wastewater was dangerous. It was all bad. Everything was negative. And then now we're trending towards this concept of resource recovery. around water, carbon, nutrients, energy, and much, much more. And so the timing between when we invented this technology and what was happening at a sort of global and macro shift in terms of how people think about design and water and wastewater also happened to be going through a pretty monumental shift. That led us to what is today the ABNR process. And this is a high-level process flow diagram that I want to share with you, but it was kind of, I'll give you a little bit of the history. So I met with one of the wastewater design engineers in Missoula, Montana, where I'm located today. And I asked him, what is your biggest problem? He walked me out to the Clark Fork River where they discharge. They have a 36-inch discharge pipe. About 10.5 million gallons a day of wastewater go into the Clark Fork River. And he pointed down to that discharge and he said, that's our problem. And I said, I don't understand. What's the problem? He said, well, the problem is excess nutrients, phosphorus and nitrogen. I said, well, why is that a problem? He walked me through the negative implications that it has in terms of taking oxygen out of the rivers, lakes, and streams, has major impact on plant life, animal life, fish life, et cetera. And I looked at him and I said, well, what if we could take the problem and turn it into the solution? And he said, well, what do you think? And I said, well, why don't we take and create an algae bloom within a controlled environment and manage that process inside the wastewater treatment design instead of allowing it to happen in nature naturally. And at that point, he said, well, shit, if you guys can do that, you'll redefine the entire industry. And so that was enough to motivate me to get excited about this concept of biomimicry and biomimic design and how we could apply traditional design principles to an innovative process and turn what was the problem into the solution by moving it upstream into the controlled wastewater treatment environment. So at a high level, the way this technology works is you've got a nutrient-rich form of wastewater that's coming in. You've got a carbon source. So algae is doing the primary work here. It's a microscopic plant. It's the tiniest plant on the planet. So if you look out your window and you see trees and shrubs, right, and you see a large pine tree, that takes 50 to 100 years to grow. Well, a single cell microalgae cell will duplicate itself every 12 to 48 hours, right? So it's logarithmic in its growth patterns. It replicates itself very quickly. If it's got a form of carbon, a form of phosphorus, there's water and sunlight or some form of light energy, then it will go through photosynthesis and duplicate itself. So what we had to do was create an environment where all of those things were present. So nutrient-rich wastewater goes into a mix well, meets up with carbon dioxide, and there's a return stream of algae that's coming from the separation phase of our process, which is the third phase, that acts as a seed stock for the process to be a continual and 24/7. Once they combine, they start to recover phosphorus and nitrogen. They consume carbon dioxide and they give back oxygen. That's what we call our biodiverse mixture flow. This is happening in a large pipe, a large tank, some type of very turbid environment where we're getting a lot of mixing in the process, and we're getting the algae in contact with the wastewater to recover phosphorus and nitrogen. From there, because light energy is the source that makes all this possible, we put it into vertical photobioreactors. And I'll show you a picture of these, but these are a vertical array of glass tubing in which the wastewater and algae are mixing and flowing through these reactors in a plug flow method, meaning they come in one side and go out the other. They don't mix in between. So it's a one-time sort of single pass-based system. The sunlight provides the energy. The algae then stores those nutrients and that carbon as carbohydrates, and then it utilizes it when it gets into a dark phase. From there, we have to separate the algae from the water. So clean water goes downstream of the of the membrane, and the algae then is returned to the beginning of the process. Now, in order to keep all of this system in balance, you have to take off the growth of the algae that occurs over that 24-hour period. So to simplify this, imagine your front yard or a lawn, a football field, or a large field of grass. It has sunlight, you give it water, you give it some phosphorus and nitrogen in a fertilizer, and you give it, it takes in carbon and it grows. It grows a little bit all the time. Well, if we were to say we want our grass to be at 1 inch at all times, we would then set that inside of our system as the amount of density or the amount of mass in the system that we need in order to recover all that phosphorus and nitrogen. And we would waste off or harvest anything that was in excess of that. So if it was growing at, a half an inch a day or a quarter inch a day, anything over 1 inch, 1 1/4, we would take a quarter inch off and we would push that into a harvest phase. That harvest then represents a plant-based feedstock that we are currently turning into bioplastics, biofoams, inks, foods and feeds, and some other specialty chemicals that have very interesting implications. But really, these are going into products that you experience in your everyday life. So the plastics and foams are going into tennis shoes. They're going into yoga mats. They're going into surfboards. So you're using these products every day, and you don't probably realize it, although companies are getting very big marketing, positive marketing implications from the fact that they're using biofeedstocks. In addition to that, for example, Patagonia just hired a company that we have an exclusive relationship with that provides ink. So ink is traditionally made from petrochemicals, right? Very carbon intense inputs. Well, Patagonia wants to remove 100% of all inks and print label packaging that had to do with petrochemicals and replace it with plant-based inks. So they've got a proprietary process that when we supply that algae, it gets converted into inks. Those inks then go into Patagonia packaging, and away you go. Now you can claim that your packaging and your labeling is 100% sustainable. So there's some really cool stuff going on the eco-friendly product side of this adventure that we've been on. To kind of bring the big picture full circle before we dive into the detail, we're taking wastewater that has carbon, phosphorus, and nitrogen, and carbon dioxide from waste streams at these wastewater treatment plants. So a lot of these plants have a massive amount of carbon dioxide that's being vented to the atmosphere, either as methane or carbon dioxide. We're beneficially using that inside these wastewater treatment plants. And ultimately, when you combine the ABNR system with a wastewater plant where there's a waste stream of carbon dioxide, we can actually make the entire waste water plant carbon negative, which is a positive thing. We use sunlight as energy. The result of that process is you got clean air, you got algae biomaterial, and you've got clean reusable water. And that's an exciting value proposition. Any questions before I dive into some of the details, Eric or anybody else?
No, I'm good. I'm following along, but anybody else who wants to, feel free to jump in.
Okay, great, thanks. So let's talk a little bit about algae-based wastewater treatment and design. These are a lot of the lessons learned, and Eric, you can speak to this as well as I can, being entrepreneurial and engineering driven and design driven. A lot of these things, we speak about them as overnight successes, but remember it's 2021 and I founded the company in 2008. So it's taken us 12 or 13 years to get to the point where we could, in a single slide, communicate to a group of engineers the biological and mechanical processes and challenges that we had to overcome in engineering something that wastewater treatment plants would be willing to implement at their existing infrastructures. So it's a big challenge to sort of get to this point. And we've taken all these lessons learned, and I'll show you how we applied them. But on a biological basis, algae cultures are native to the treatment plant that we work with, and the ecological region that we implement these systems. And so they will outcompete the other biology, right? It's kind of like a biological clash of the titans. Whoever is more dominant is going to win. And our job is to create an optimized environment where the algae outcompetes every other form of biology within this system because of the conditions that we give it. And uniquely, as we were designing all of this, because I come from an information systems background, we wanted to make sure that we were designing systems that would manage the information systems would be intelligent enough to manage the mechanical process in relationship to the biological's performance, so that you could marry the two of those and make on-the-fly adjustments to the various conditions to ensure that you've got the most optimal environment for algae growth and algae competition to outcompete the other biology in the process. So algae are also preconditioned to changing environments. Remember, they've been here for 3.8 billion years, so they know how to evolve inside of these environments. Uptake rate definitions take many, many forms, and this is a critical component when you're talking about designing algae-based systems. Nitrogen species definitely impact the kinetics and specific uptake rates on how you look at recovery of nutrients. Higher phosphorus concentrations as milligram per liter are equal to higher P percentage per cell. So if you took a single algae cell and you had higher phosphorus concentration, say 2% or 2 milligrams per liter versus 1, the P percentage per algae cell would be higher in the 2 milligrams per liter versus the 1. That's a critical component in the design process. System algae mass plus our percent P per cell will drive our kinetic assumptions. So in the modeling of this, when we compare it to some of the other systems that people use to model wastewater treatment plants, like BioWin, which is a software platform to simulate and model wastewater treatment plants, these kinetics are very, very critical to that. And then, of course, we're using the Redfield ratio, which is carbon to nitrogen to phosphorus, to really drive the overall biological performance. On a mechanical basis, we really had to work a lot on light distribution, intensity, and what the light versus dark cycles were going to be in this technology. So algae require light, and they require it 24/7. So at night, we have to light those systems with artificial light because the treatment process can't stop at night. We also had to understand how far we could push the kinetics and the dynamics of how the algae would respond to changing conditions. So if you think about an algae cell and you put it in its natural environment, the sun comes up at 7 o'clock in the morning and goes down at 7 o'clock at night. That's a 12-hour exposure. So 50% of the time it's in the light and 50% of the time it's in the dark. What we did is inside of these systems, because the hydraulics work the way they do, we're actually supercharging that process so that we go between light and dark anywhere between like 6 and 10 times a day. So the algae is going through this process in a hyper efficient way, and we had to learn how far we could push that from the standpoint of still maintaining the growth rates that were necessary to recover the nutrients that are in the wastewater. So that was a big challenge, and it still remains something that we continue to optimize. We had to look at flow rates and velocity minimums. So we don't want to get laminar flow inside of our tubing systems because we need a diverse and mixture flow running through the piping system so that the algae accesses light and then it can go through photosynthesis, duplicate itself, and then access light again. If it were laminar flow, then everything on the outside of the pipe would be getting light and everything on the inside of the pipe would not. And that's not what we need. We need light access to every one of these cells as much as we can possibly achieve. in this process. So we had to design reactor systems that allowed the light and the mix to be really efficient. We studied carbon dioxide sources and uses. We talked about that a little bit. We had to figure out separation and membrane filtration. So other than you, Eric, I don't know anybody who's broken or chewed through more membrane systems than Clearis, because we were in search of what's the perfect application for this. We used pressurized systems, we used hollow fiber, we used cross-flow membrane systems. We used so many different methods to try to look at what was the most energy efficient and effective way of separating these microscopic solids from the water. And ultimately, our research landed on these submerged membranes. They're fairly low cost and pretty energy efficient, but we're always in search of that. The other thing is, in wastewater, we have a definition or an acronym called SRT, which is solids retention time. This is the amount of time that a single algae cell spends inside of our system. So in traditional wastewater, that SRT, when you're using bacteria and other things that are at most plants, it's going to be anywhere from 10 to 20 days, maybe 6 to 10. Our algae only spends 1.5 to 3 days inside of our system because the growth rates are so aggressive. And so that's a major component in understanding how do you design for these wastewater treatment environments. And then obviously automation and controls was a big component of how do you take all of these lessons learned and put them into a system that automatically manages and controls the overall process. So let's talk a little bit about how we do that. There's 3 methods of uptake rates that we could apply to the algae. One is a specific loading rate, which is pounds P fed on an F to M ratio. So pounds of P divided into pounds of algae TSS per hour. The second would be a concentration-based specific uptake rate, which is milligrams per liter of P removed over milligrams per liter of algae TSS per hour. And then we use what is most common in the industry is a mass-based specific uptake rate, which is the pounds of P that we recover over the pounds of algae per hour. And that's what drives our modeling system. So when customers come to us and say, can you design a system for us? We say, yeah, we're going to use a mass-based specific uptake rate process. And you can see it here on the chart. I just put together a chart that has, 5 or 6 different facilities that we did some testing at. But on the vertical axis, you can see the specific P uptake rate, which is the pounds of P removed over the pounds of algae per hour. And down on the horizontal axis, you can see the influent phosphorus, which is in milligrams per liter. So this specific phosphorus uptake rate, when we do our pilot testing, we will test their water in contact with algae, and then we'll run kinetic studies that look at how long does it take to reduce the phosphorus over time. And ultimately, that results in a specific uptake rate number that we can use for our design basis. So once we've gotten that, we gather other key inputs and we apply the kinetics from this experience. So we take the feed flow, which is the gallons per day. We take the feed phosphorus and nitrogen concentrations and what we want the effluent concentration to be. We make some assumptions around what the algae suspended solids are going to look like inside of our system. And then we assume a % P per algae cell. So once we've got all that data, we can calculate our total process volume that's required, which is the pounds of phosphorus per day divided by our algae density, which we selected as 1,000 milligrams per liter here, times 8.34 times the spur. And in this case, our average spur across all systems is 0.00052, meaning that is the amount of pounds recovered over pounds of algae TSS in the system. And because we know that, we can design for what the sizing and loading of these systems is going to be. Once we've got that, we split the volume 60% into the mixed tank, which is dark time, and 40% into the photobioreactor, which is light time. And that then gives us our basis of design. To give you an example of that, let's look at the village of Roberts. So this is in West Wisconsin. There's 1,800 people. It's a 465,000 gallon per day system. They currently discharge 1 milligram per liter. They're going to have to get to 0.04 phosphorus. I mean, that's orders of magnitude difference. And they've got to get into compliance by January 1 of 2021, which was, a month and a half ago. They did look at some alternatives. They looked at chemical alternatives. Ultimately, they looked at ferric, alum, cerium chloride. They looked at ultrafiltration systems, and ultimately, our technology was what proved to be the best. So why did they select us? Well, total phosphorus and ammonia recovery recur within the system. And then you get all these other ancillary benefits that come along with it, including an algae co-product that provides them with a recurring revenue stream that they can count against the total cost of ownership of their investment. So let's take a look at the village of Roberts' basis of design. It was 150,000 gallons. We were feeding it 4 milligrams per liter of phosphorus. They needed to get to 0.04. The average specific uptake rate is 0.00052. That's pounds of P fed to pounds of biomass per hour. And we are going to operate this system at 1,000 milligrams per liter. What we ended up realizing was that we would need 120-minute process time. So 72 of those minutes is now in a mixed tank dark time. 48 of those minutes is now in the light time. And we're lighting these systems at night with 1 watt per gallon of light. And we're assuming that we can duplicate that algae once every 24 hours. So the results are actually, we've been feeding it 3.5 milligrams per liter. We've been achieving 0.02 milligrams per liter in the discharge. And we've been running the system at 900 milligrams per liter of algae. So slightly different than what we designed it for, but still the kinetics are exactly as we would have expected. So we are seeing the average loading rate at 5.2, and we're seeing the uptake rate at 5.2. This facility is producing 300 pounds of algae per day. We're recycling or sequestering 660 pounds of carbon, and it's fully operational at this point. So this is the output of what is probably a 50 tab engineering and design basis that says these are the inputs. This is what we expect to happen, and here are the results we achieved. To give you a sense of this system and how it was designed, here was just the overall site layout. You can see the existing infrastructure that's already there. You've got 3-stage SBR on the right side of the page. You've got some mechanical buildings on sort of the center left. And then all of the stuff sort of up above that is where our technology got implemented. To show you what that looks like, you can see on this picture on the far left is the mix tank, right? So that's where their secondary effluent meets our algae. It mixes in this tank. It goes into the photobioreactors, which are on the far right side of the building, the process building. Those are the vertical array of tubes where the algae and wastewater are flowing through it, accessing light. And then it goes back into this mechanical building where it gets separated. This small tank below the mixed tank is the carbon dioxide feed, which is coming from a local ethanol plant. That ethanol plant is now getting carbon credits for supplying this and sequestering it inside of that algae. So just to give you a little look at, and we're going to go through these fairly quickly, we ran into some big challenges building this system because we built it during COVID and in the winter, which would never be recommended in Western Wisconsin. But that's what we did. You can see how the mixed tank is going up here. It's a 53,000 gallon tank. We'll use half of that for our phase 1 approach. There's the tank itself. What's cool is the engineering and design that went into this tank. So this is the water that's coming back into this system from the separation system. So this is the algae that's feeding the system. It's coming in here. and it's designed hydraulically so that it comes across the bottom of the tank and gets pushed up to the top of the tank, therefore taking advantage of the total retention time. These metal or bars right here are actually air systems that every once in a while shoot air into the bottom of that, and it creates a turbulence so that the algae stays mixed inside of that environment and we don't get any settling inside of the system. And then this, you can see opposite of where that pipe comes in is a hole. That's where it's being pumped back into the photobioreactors to go back out and get some additional light. Here you can see the inside of the mechanical building with a bunch of feed pumps and the various effluent backwash pumps that are associated with the membrane tanks. Here you can see these are the air systems. So this will compress air, and every 30 seconds, it will throw a blast into the various tanks that exist so that we don't get algae settling inside of those tanks. If algae were to settle inside of those tanks, it would go septic. And when it goes septic, it would release its phosphorus and nitrogen. So we've got to keep things in suspension within this facility. Here you can see the harvest mechanism. This is the algae that we're taking off every single day to keep the system in balance. One thing that's really cool about this is, as you can see, I'm going to skip forward one page. This is the vertical array of tubing. So bottom left, wastewater comes in that bottom left of that, what we call a vertical fence. And it flows from left to right and serpentines up to the top. Well, we had to invent a way for these pipes to get cleaned on a regular basis. So we invented a pigging system, and that's what you see in this picture. Those gray boxes are the automation and control system where we're pushing air into these valves. These valves are actuated with that air. And then inside, just to the right and left of those gray boxes, there's a little pig in there. And that pig gets released every 2 hours. And through using the velocity of the system, it drops in and flows through that and spirals through the entire plant in order to scour these pipes so that it stays clean and we get excellent light transmissivity. Yep, Eric.
So by pig, you're not talking about a little piggy. You're talking about like a slug, solid slug thing that like pneumatically shoots through there and sort of brushes the glass clean, right?
Correct. Yeah. So it would look about the size, take like a 12-ounce Coke can. That's.
Are you going to show the picture or not? Because I know that's where some of your IP is.
Yeah. Let me see if I, let me know if I, let me see.
Don't show us anything, confidential or proprietary.
No, I don't have, I was going to say, let me see if I have one in my office. I don't have one, but it would be about the size of a Coke can, just wider diameter. And then imagine a toilet brush with the brushes on the outside. That is what this system is. It's weighted. It's open on the back end, so it just gets pushed by the velocity of the flow within the system. But yeah, it's spiraling. We invented it so it's rifled. So the brushes are rifled, so they don't go straight. They go in a rifling manner. That way, it automatically, rifles through there and scours the entire system. It's really cool. I mean, I can remember the first one we created was a $1 toilet brush from Walmart hooked to a fishing line leader that had a tennis ball that we dropped some weights into in order to create enough a weight for the system to sort of scour the entire system. And so we've come a really long ways, but it's a really cool invention. And the IP is honestly in how these controls work in order to launch these pigs and then get them home into these pig homes, right? So it's a fairly sophisticated level of programming and know-how, because a lot of the pigging systems would they don't work in plug flow reactors like we've built, because you can't if you were to design it a certain way, you would allow water that hadn't been fully treated to go through the system otherwise. So it's always been one of the biggest challenges, and it's really a cool and efficient design. Here you can see these are about 14 feet tall, and they're 140 feet long. So water is takes about 50 minutes for the water to come in and exit that. Once it exits the photobioreactors, it's going into the separation tank. There, you're separating the algae from the water. The algae is being returned to the mixed tank to start the process over, and a portion of it is taken off into harvest, where it's dewatered and dried to go to market. This is
Jordan.
Yeah.
Jordan, quick question. Your tubing there is providing the residence time, right?
Yep.
I'm just asking, theoretically, could you go taller and make it shorter? Or
Yes.
is there a limit height-wise for some reason, structural or operational?
The only real limit we've come up with, Eric, is going to sound very practical, which is operator maintenance. So
okay.
The next system, the system that's under construction right now, is actually 20 feet tall and 100 feet long because they had constraints. But you're right, it's just it's a contact time between the algae and the water, and you can kind of use it like Legos and fit it to whatever circumstances you have at the facility from a footprint standpoint. So you can go taller and less length, or you could go shorter and more length, as long as you have the retention time that you need between the algae and the wastewater in order for those kinetics to kick in and take up all that phosphorus and nitrogen. Everybody likes to see what this looks like at night. This is what it looks like at night. These are the LEDs that kick on when the system senses that a certain light reading has gone below that which is acceptable for algae or plant growth. In this case, we use what's called a PAR sensor. PAR stands for photosynthetic active radiation sensor. And it's just a reading of how much is available to the plants in order for their growth. So that lighting system kicks on at night, and we can treat 24/7. Here's another look at the system. You can see there's there's 5 feet of space in between these different fences. We actually inoculated this using our South Davis system in Utah. So what we do is we take an inoculant, we spin it through a centrifuge, it looks like toothpaste, and then we pour it into this system, and within probably 48 hours, it starts to take off. And this is a cool picture. It shows you, here is day one on the left. That is the algae, and you can tell it's very almost clear, just a tint of green. So you know there's not that much in there. On day 5, here's what the reactors looked like. And then on day 8, the reactors were about 50% of what we wanted in order for treatment to take place. So on the left, we were at about 12 milligrams per liter. And on the right, we're at 400 milligrams per liter. It took us 8 days to get there. So those are the kinetics and the specific uptake rates that we're managing in order to design these systems and apply the math models and the design principles that we've learned over the course of the last decade, and how to put that all together to manage a flow rate that's coming at you on a 24/7 basis. I talked a little bit about the instrumentation controls. This just shows you the simplicity of a large system, but we believe that good information systems and control mechanisms allow you to implement what would otherwise seem as very intimidating technology. When you're working with municipal and industrial wastewater operators, new is not a word that they like to hear. So having technology that operates and functions very similar to their existing platforms is a critical step in making sure that we can deploy these types of systems. So it works and is managed almost identically to the systems that they're already running at their wastewater treatment plants. And then here's a quick look at, just so you got a sense of it, what the algae looks like. On the left is the dewatered. That's the stuff that we would inoculate systems with. That's coming out of a centrifuge. On the right are actual pellets that were dried through in this case, it was a microwave dryer, but those are pellets that are actually displacing EVA, traditional plastics, and are now plant-based algae plastics. Those are the ones that are going into the foams and plastics industry now. Just to give you a sense of some of those products, shoes, fertilizers for plants, fuels. We don't focus much on fuels ourselves. Others do that. Proteins is a major market, and we're working in that space. And then also some specialty chemicals. We actually have a pilot plant going in Roberts, Wisconsin right now to generate biosuccinic acid. And it's a base chemical that's used as a lubricant and in a lot of different industries. It's one of the 12 most important chemicals that the US has defined as must need or have to produce in the future on a much less petrochemical based intense process. So we've got some trials going on conversion of algae to biosuccinic acid using some interesting and proprietary technology that's pretty cool. So this kind of gives you a good sense of what do we do with that co-product and why is it important in the overall scheme of what we're doing. And I think that's it.
Such a great presentations. We have lots of questions actually, students. Student ask, and I actually stopped them to ask question in between because there are so many questions.
Okay.
So I would ask the student who I think she already wrote on the chat windows. There are 4 questions. If you can read them.
Kashitya, you want to go ahead and kick us off?
Yeah, sure. I listed on 4, but I think other students can also ask in the middle of you answering all my questions. But it was basically, my first question was about, like, for example, in phytoremediation, we have a symbiotic relationship between bacteria and the plant roots. Would there also be a similar functionality between algae and bacteria here? And I guess my next question is also kind of related to the bacteria growing. You mentioned that the algal growth was optimized in these systems, but I just wanted to know that there's a certain conditions that would be optimum for bacteria and the algae. So would increase in turbidity affect nutrient uptake or the light passing through to the algae?
Great questions. Okay, so let me answer your first question, which is in relationship to bacteria. So yes, there is a symbiotic relationship. So in the traditional secondary treatment process of wastewater, you use bacteria to really remove carbon from the system and to nitrify. So you're taking and converting ammonia into nitrates and nitrite, right? So that is the primary concept around secondary treatment within these wastewater treatment plants. There is a symbiotic relationship. The interesting thing about what we've done is we've sort of disrupted the secondary treatment process because we would actually prefer to not nitrify. Because ammonia is more readily available to plants, because it doesn't require a chemical conversion within their cell structure, then it can use it faster. So the uptake rates of phosphorus are best when ammonia is the nitrogen source. So while we have bacteria in the system, we're actually trying to limit the amount of nitrification occurring, and therefore reducing oxygenation in the system is critical in order to maintain optimal performance. The other piece to that is that a lot of engineers that look to add our systems to their facilities are moving upstream and detuning their secondary treatment process so that they're focused primarily on BOD and total suspended solids removal in the secondary process and limiting the work of the bacteria, which also reduces the overall energy cost of the plant, because in order for bacteria to work, they've got to have massive amounts of oxygen. And therefore, you can eliminate that oxygen use in the secondary treatment process because we'd prefer to have the ammonia anyway. So they use it as a contact stabilization phase as opposed to really a nitrification stage when we implement our solution. So, yep, there's definitely bacteria in our system. The algae outcompete the bacteria because we're creating conditions where that occurs, but there's definitely a symbiotic relationship there.
And then would this also apply to like anaerobic or anoxic bacteria?
Yes, same principles. Yep.
Okay, thank you. I can ask the other two questions later if
Go-
there's any questions.
Go for it. Go ahead.
Okay. So my other question was about, you mentioned that you want to make sure that the light passes through the pipes to reach the algae. And I was just wondering how that would be possible with what material you use for the pipes, or it reaching all of the algae equally. And then my last question was about uptake of phosphate and nitrogen and how you would test for that. So would it just be testing or checking the biomass of the algal cells? Or do you also just check the influent and effluent? Although I'm not sure if there's other species inside of the reactor that would be also taking up phosphate and nitrogen. So how would that affect testing for uptake?
Yeah, so I'll answer your second question first. We do test the incoming phosphorus and nitrogen in its various forms, as well as the effluent phosphorus and nitrogen, to be able to confirm and calculate what the overall specific uptake rate is within the system. So we have online, basically real-time monitoring of those systems that are talking back to the information systems and allowing us to make adjustments if necessary. So that is something that is automated and built into the overall process. And if we are nutrient limited in any way, there are systems that automatically will add additional phosphorus or nitrogen if we're out of balance from a C to N to P relationship. So, and those are different. Those are typically organic feed systems. So at most wastewater plants, they dewater sludge. Well, when they dewater the sludge, it's really high in phosphorus and nitrogen. We keep a tank of that available to supplement if we get out of balance in terms of our relationships between C to N to P. So that is the answer to your second question. From a light transmissivity and penetration standpoint, the unique thing here is that we're talking about microalgae, and the overall weight of algae and so an algae cell and water molecules are not very different. And so inside of that pipe, there's a ton of mix that's occurring, and it's why we built the elbow systems the way we do. So those elbow systems actually have some proprietary components in them. And to simplify it in today's terms, and y'all are college students, so you'll know this. Remember when Miller Lite came out with a beer bottle that had rifling at the top so you could drink it faster? If you don't remember that, it was a big deal. But the inside of those pipes, actually, so when you go around that, it's rifled so that it forces the water to mix every 140 feet. And therefore, you're getting a good mixture flow through it. What they measure—
Your technology is built on your fraternity days. Drink, fun drinking games.
Yeah.
I have to drop off, Jordan. I have another thing, but this was amazing. Thank you so much, and we'll connect later on. Okay.
Yeah, cool, man. Thanks.
All right. Take care.
Thanks, everybody.
No, you can stay on, just me.
Oh, okay. Okay, I gotta wait.
I guess, we end the seminar around 1:50 to 2 o'clock within that time, because many students have class after 2 o'clock. But I asked the students if they have questions, they can stay and ask you. Unless you really, have some other meeting, you can leave, of course.
I'm good.
I
I'm
think
good.
we have another raised hand. You guys ask questions, go ahead, and if you want to.
Hi, Jordan. Good to meet you. This has been a great presentation. I had a question just in maintaining that red field ratio. So are you within the solution, within the water, you're maintaining 106 to 16 to 1 for CNP?
Yeah, we do it on a mass basis. So it actually works out to be 1 to 8 to 50.
Okay.
So
8 to 50.
one part phosphorus to
Right.
8 parts nitrogen to 50 parts carbon. Will you cover me? Give me a half an hour. I'm just finishing up. Sorry, I've got one of my employees that needed something. Yeah, I know. Tell him I'll be 30 minutes. Thanks.
Great, thank you. So do you guys have any challenges with maintaining that carbon ratio?
Not traditionally, and actually it's an interesting concept. So we use carbon for 2 reasons. Number one is as the sugar source for the algae, but also because we want to be able to maintain a certain level of pH within this system. So what we typically see is when pHs in a wastewater plant exceed 7.6, you'll start to see some negative implications around bioavailability to the algae. So you'll get like calcium phosphate bonds, for example. And now that phosphorus, which is bound to calcium, is no longer bioavailable to the algae. So we use it as a buffering mechanism to keep the pH at a level where the carbon and all of the nutrients are bioavailable to the system. And if we ever encounter situations where we think there may be a bioavailability issue, we'll crash the pH in the mix tank or prior to the mix tank for the effluent that's coming in. We'll take it to like 6 or 6.2, and you can do that using carbon dioxide, or you can use, some other acids to do that. But it frees up all of the phosphorus and nitrogen that makes it accessible to the algae. So we don't have a difficult time maintaining the carbon relationship because we've generally got more than enough carbon, but we're using it in more than just one way in the process.
Got it. Thank you.
But
I have one last question, at least something that I learned from my students recently, and that algae could be microalgae and macroalgae, or different types of algae. How do you determine what algae to use? Or this is something people will buy, that this species of algae is much better at recovering nutrient than other?
Yep. So I'm going to give you a non-scientific answer to this because it's all I understand. So when I first got into this business, there were some folks who were doing both directed evolution and genetic modification of algae strains, both macro and micro, and thought that that would be the best approach to take. So at our first pilot study, we took a sample of algae we had purchased that was designed for wastewater treatment. And then we also just took a bunch of water from the secondary clarifier at the treatment plant. We set up 2 independent systems. In the system that we attempted to select algae that would best perform, the algae that we purchased was eliminated within 1 SRT, meaning within 1.5 to 3 days. And it was replaced by algae that was native to the secondary clarifier in the system. So we learned a valuable lesson really early in that process, which was don't try to outcompete Mother Nature in that environment. She has already done it. The species that are successful are already living in the environment. All our job is to do is to give it an environment that optimizes its ability to grow and then get the heck out of the way. Trying to evolve that or self-select or select for those is a really, really challenging task. And I honestly don't think it would work in an environment like this because, you know, at a lot of these plants, for example, the one we're building in Salt Lake, it's 6 million gallons a day. You have massive amounts of solids, bacteria, and algae that are all coming through that system on a regular basis. And you can't possibly keep the bad out and only select for the good as defined by yourself. You've got to just be able to accept what's coming at you.
Yeah, I think that's something we keep really learning for even bioremediations. I think
Yeah.
Kevin has another question, or Kevin, you want to ask a question?
Yeah, sure. Thank you. One last thing, what has made your company more competitive than any other company out there in terms of staying alive through, I feel like there's a major boom in this industry and a lot of companies succeeded, a lot failed. What has allowed you to stay afloat and succeed?
Well, you know, I think one of the things that helped this business is my background is I'm a serial entrepreneur. So this is my 6th company. Not all of them were successful. Many of them, you know, I've got about a 50% hit rate. And, you know, that's pretty good compared to, you know, maybe 1 out of 10 successes. But I think just experience and also realizing that we had to put technology into the market before it was ready and test it in live environments, because there's a tendency to want to over engineer, over design, over evaluate all of these solutions. And none of it matters when you stick a pump into a clarifier and start treating water. And I think that's the thing that we learned really early on in this business was, A, we got to get the technology into the market as quickly as we possibly can. B, we're never going to provide something without getting paid for it. So in my experience, free is not a solution. People will take anything from you. What we want to do is make sure that there's a pain point that's sharp enough that somebody's willing to write a check to solve the problem. So because I also do some adjunct teaching at the university for the master's program in entrepreneurship, the biggest challenge I see over and over is you've got inventors and entrepreneurs who have a solution to a problem that doesn't exist. In other words, there is not enough pain in the marketplace to drive economic decision-making where people will open up their wallet and pay money to solve that problem. So we get lots of circumstances through these business schools and these, we've now partnered up with Montana State University Engineering, where we're getting really cool solutions that will never scale commercially. They won't, nobody, when you say, well, how sharp is the pain and how much is somebody willing to pay to solve that problem? You kind of get a deer in the headlight look and they're like, well, I don't know, but it's cool. Well, yeah, it's damn cool. But if it doesn't make something more efficient or it doesn't connect with a value proposition that people are really, you know, in tune with, like sustainability, which has become more than I could ever have imagined. I mean, 20 years ago, the concept of sustainability was so far reaching. 10 years ago, it was all marketing dollars. And now some of the largest capital sources in the world have come out, like BlackRock, and said, if you aren't an ESG-based investor or technology or company, we're not going to invest in you. You have to have sustainability at your core. And that's a dramatic shift in these marketplaces. So in answering your question, 1, we got it out in the market. 2, we made sure people were willing to pay. And 3, we got incredibly lucky around timing and sustainability, because a lot of times timing will kill these businesses. We just happened to survive long enough and keep our overhead and our burn rate low while we had strong investor participation to get to the point at which now people are willing to pay for sustainability. And 10 years ago, it was not something that people would pay for.
That's such a good questions and something that we staying in academia, we don't learn that much, and so it's great to have someone like you as a speaker. I think we have another question if you have time.
Sure.
Mark, you want to go ahead and ask the question?
Hey, Jordan, thanks for the presentation. I was just wondering if you could talk on some of the geographical limitations or incentives of the ABNR system, like coastal California for where we are, for example, or Wisconsin.
Yeah, well, selfishly, I wish we were doing more of these in Southern California because I'm tired of going to Wisconsin in December, January, and February. I can tell you that much. So interestingly enough, we have not experienced, so we're kind of doing this in the worst case environments right now where sunlight and temperatures are fairly extreme, meaning we get way less light and we get a lot more cold than y'all would ever experience. So ironically, we're testing these systems in areas that are pretty extreme from that perspective. What you've got to remember is, and I was just looking at this data, I was out there last week, the wastewater treatment plant effluent temperature is about 55 degrees Fahrenheit. So we've done this in environments where we've had to break the ice and pump it out of a lake and been able to treat the water. So 55F is a pretty darn far cry from freezing temperatures. So that's good. And then, on a sunlight basis, because light energy really drives the entire process, we're using a bit more energy in the northern climates than we are in a southern climate. But if you were to pick the perfect case scenario, you'd have 70-degree temperature with 70-degree Fahrenheit sunlight 18 hours a day. That would be the perfect growing environment. And then every move, longitudinally north or south of that is, going to have a little bit of an impact on performance. But we're able to manage that through, LED lighting systems and just managing the overall control process. So in the winter months, you reduce the amount of algae that you waste off the system because the kinetics slow down. Just like we slow down in the winter, we don't eat as much in the winter because we're not moving as much. So the algae do the same thing. Colder temperatures, less light, they slow down their kinetics. So we just slow down the waste rate. In the summer months, when it's warm and they're getting 16 hours of natural sunlight a day, we're actually increasing the waste rate because we've got to get solids out of the system. So that's the management relationship that exists as you kind of move north and south from the equator.
Awesome, thank you.
But
One last question, because this is such an interesting challenge and problems come up with the solutions. I was yesterday I learned that these Hyperion wastewater treatment plants in Los Angeles has almost like 500 million of I think gallon of water treated every day. So
Yep.
The question is, if you want to scale this up, at what point, or how much gallons of water you can treat per day? Assume that you have energy and all that. Let's say in California climate, or how much water you can treat per day at a facilities.
yeah, today I'm comfortable saying that we could probably do up to 20 million gallons a day.
Okay.
Which is a long ways from 500 million gallons a day. We have been working with Chicago, city of Chicago, which has the largest wastewater plant in North America. And they're looking at, it's almost 1 billion gallons of water a day. The footprint becomes the challenge, especially in California or some of these major metropolitan areas. So finding the land space to do this is a critical component. But I would say from a design standpoint, 10 to 20 million gallons a day is probably a comfort zone for us right now. I don't know that we'll ever be at those larger scales because at those larger scales, you've got civil infrastructure and populations that are so high that this technology probably would never fit within the footprint or available footprint that you have.
I was just thinking when I see your design that all these like a wall, this could be this could be the great wall, separating different state and use this
Yeah,
for different
yeah.
systems.
We could build it on top of buildings, but
Yeah.
that would be a big engineering challenge.
Yes, yes. Well, I guess you got to have some of your breath, with all this longer time. I appreciate that you stay back, and I'm sure students appreciate really having you here. And
Sure.
I'm going to share these slides and particularly talk with my classes and other students because they are really interested in this topic. Well,
Great.
thank you so much. As I said, this is a pleasure to have you here today.
Thanks, everybody. I really appreciate it. Take care. Let me know if there's anything you need from me.
Yeah, great. Thank you.
Awesome.
Thanks, Jordan.
Thank you so much.
Thank you.
Thank you.